Okay, in this section, we're going to see a particular category of substitutions called trigonometric substitutions that are designed to handle a particular category of integrals, namely an integral that has a sum or difference of squares in it and where no other u substitution or technique like integration by parts presents itself. So as an example, let's take a look at this guy. So here's an integral, and if you try to do a u substitution here, you'll find that there isn't really an obvious one. If we had an x in the numerator, then, well now you could just let u equal 1 plus x squared, so du is 2x dx, and we're on our merry way with this. Okay, and you may think, well, if there's no u substitution, let's try integration by parts. Well, if you do try that, you're going to find this is very difficult as well. So instead, what we have is this class of particular substitutions called trigonometric substitutions that take advantage of this particular structure right here. 1 plus x squared looks a lot like Pythagorean identities. So if we recall the Pythagorean identities, we have cosine squared of theta plus sine squared of theta is equal to 1. We have 1 plus tangent squared of theta equals secant squared of theta, for which there's the convenient mnemonic, I tan secretly. And we have 1 plus cotangent squared theta equals cosecant squared theta, whose mnemonic is 1 coat in the closet. So when you have a sum or difference of squares in an integral, and there's no obvious u substitution, well, we're going to try and make this 1 plus x squared here look like one of these identities. In particular, imagine that this were 1 plus tangent squared. Well, then the entire radical would be secant squared. But the square root of that would just be secant. Okay, so let's see how we would approach this and what a trigonometric substitution is. So for a trigonometric substitution, we would do something like let x be a trig function. For instance, in this case, we're going to let x equal tangent of theta. So our dx is secant squared theta d theta. Now, one thing that distinguishes this from u substitutions is we normally, with a u substitution, we let u equal an expression involving x. And with a trigonometric substitution, it's usually the other way around. We're going to let x be some expression involving theta. Another thing that we need to pay close attention to is the fact that this is not a well-defined substitution. Well, what do I mean by that? Well, normally when we let u equal something, like say 2x, for each x value, there's exactly one corresponding u value, so this is well-defined. However, in this substitution, we are not well-defined because for each x value, you can have many corresponding theta values. For instance, if x is equal to 1, a corresponding theta value would be pi over 4, since tangent of pi over 4 is 1. But another corresponding theta value would be 5 pi over 4, since tangent of 5 pi over 4 is 1. Okay, so to get around that, we're going to just impose a quick little restriction here. We're going to say that theta is between negative pi over 2 and positive pi over 2. Okay, so now let's go back to our integral and see how things have changed. So here's the original. And now let's replace each piece with something in terms of theta. So we have dx, which is directly secant squared theta d theta. Notice we didn't have to solve for dx. Because of the way we do a trig substitution, our dx is naturally isolated. So that is one nice thing about this. And we will divide by the square root of 1 plus x squared. But that would be 1 plus tangent squared of theta. Okay, well, why did we do that? Well, that's because 1 plus tangent squared is indeed secant squared. So we have the square root of secant squared theta. Okay. But the square root of secant squared is, now you might want it to be secant, but it's not quite secant. It's actually the absolute value of secant. Oh, that's pretty annoying. So keep in mind that the square root of a quantity squared is not the quantity, it's the absolute value of the quantity. Okay, but no problem. Because in this particular situation, we can throw away the absolute values. And that is because by the restriction that we imposed on theta, we know that theta is between negative pi over 2 and positive pi over 2, which means theta is either a fourth quadrant angle or a first quadrant angle, and secant is positive in the fourth quadrant and the first quadrant. So we don't need the absolute values. So this restriction wasn't just imposed so that we have a well-defined transformation from x over to theta. It was also specifically imposed so that after applying a Pythagorean identity, we would have a positive valued trig function, and therefore the absolute values would not be necessary when taking the square root of the square. Okay, returning to the problem here, we have secant squared over secant, which is of course secant of theta. And so all we have to do is integrate secant of theta. Well, we know that the antiderivative of secant is ln of the absolute value of secant of theta plus tangent of theta. All right, well, we finished the calculus part of the problem. However, the original problem was in x, and we of course are going to need some sort of algebraic answer whose derivative is this thing. So how do we convert our final answer back in terms of x? Well, we're going to look at this particular substitution, let x equal tangent of theta. So what was the original substitution? It was x equal tangent of theta. All right, well, looking at our solution, that's great. We have a tangent of theta right here, which we can just replace by x. But what about secant of theta? How do we convert that in terms of x? Well, we're going to need a triangle. Okay, so what we're going to do is populate the sides of this triangle according to the fact that we know x is tangent of theta. So first we'll place a theta on the triangle. And we know that tangent of theta is x, which means we will label the opposite side as x and the adjacent side as 1. So using SOHCAHTOA, we can see indeed tangent of theta is x. And using the Pythagorean theorem, we can find the missing side. In this case, that's the hypotenuse. And at this point, we can read sine, cosine, tangent, whatever, off of our triangle. So here's where we left off. Now we can read secant of theta and tangent of theta off our triangle. Well, secant of theta is hypotenuse over adjacent. And tangent of theta is in fact just x, right? It's opposite over adjacent, or you can of course see that tangent of theta is x from the original substitution. And now we have a solution in terms of x. So we're just about done, but there's one more simplification here, and that is simply noting that in this particular example, this expression inside the logarithm is naturally positive, which means we do not need the absolute values. We can convert to parentheses. So it may not be obvious that this expression is naturally positive. However, if you convince yourself that this square root expression is always a little bit bigger than x, and the square root expression is always positive itself, then that would be enough to convince you that whether or not x is positive or negative, if you add these pieces together, the whole thing should be positive. For instance, if x is negative 5, then 1 plus the square of negative 5 is positive 26. And the square root of positive 26 is a little bit bigger than 5. So something bigger than 5 plus negative 5 is a positive number. So no matter what, this expression is positive. this is our final answer. Okay, so before we go into another example, let's look at what the suggested trig substitutions are depending on whatever situation you're facing. Like, why did we choose specifically x equal tangent of theta in the last example? So it really depends on what type of form you have in the actual integrand and what identity it closely resembles. So when it comes down to it, there are really only three different expressions for which we would induce a trigonometric substitution. So let's see what those are. All right, if you have a difference of squares, a squared minus x squared, then the suggested substitution is to let x equal a times sine of theta. Now, a is a constant here, so this would be, for instance, if you had something like 16 minus x squared. Then the suggested substitution would be x minus a squared being 16 tells us that a would be 4, so this is our suggested substitution, x equal 4 sine theta. And why does that work? Because once you make the substitution, you'll have x squared in here, and x squared is 16 sine squared theta. You factor the 16 out of the radical, which emerges as a 4, and we get 1 minus sine squared theta. Okay, 1 minus sine squared theta we know is cosine squared theta, so we would get the square root of cosine squared. And you can see that simply by using this specifically prescribed substitution, we have constructed exactly the form that we want. We want the square root of cosine squared. In fact, what we really want is cosine there. So we would have to impose a further restriction here of negative pi over 2 to positive pi over 2 so that we can guarantee that our cosine of theta is positive. And the identity that's being used here is cosine squared theta is 1 minus sine squared theta. Okay, the next expression that we might encounter is a squared plus x squared, so the sum of squares, and that was the first example we saw today. And the suggested substitution would be x equal a times tangent of theta. And we saw that this was the suggested restriction because the identity that we're using is secant squared is 1 plus tangent squared. And we want to make sure that our secant of theta is positive. So if we let theta be between negative pi over 2 and positive pi over 2, that'll do the trick. And finally, the third case is x squared minus a squared. And note this is not the same as the first case because here it's inverted. The variable of integration being squared is first minus a constant squared. The suggested substitution in this case is a times secant of theta. And the identity that's being used is tangent squared of theta is secant squared of theta minus 1. So we would like to guarantee that our tangent of theta is positive, and therefore we're going to choose theta in the first or the third quadrant. So it's a little bit funky, but we're going to say that theta is from the first quadrant, so between 0 and pi over 2, or the third quadrant. All right, I think it's important that we acknowledge these intervals once, but in practice, we aren't going to write them down every time we're using these substitutions. We're going to just imply that we're using these specifically selected intervals. Okay, and a couple more comments. First is, while we are assuming the constant is being squared here, a squared doesn't have to be a perfect square. So you could have something like 3 minus x squared, and here your a squared is like 3, so your a is rad 3, so the suggested substitution would be x equal rad 3 sine theta. Okay, and the other comment that needs to be made is that you actually don't even need the square root for the trig substitution to work. So as a quick example, let's evaluate an antiderivative that we are very familiar with. We know that the solution to this is inverse tangent, yet we've never had a way until this moment of producing that result. We've always just known this is inverse tangent because we know the derivative of inverse tangent is 1 over 1 plus x squared. But let's now generate, using a trig substitution, the actual correct answer. So notice there is no square root, so this is a good illustration of the fact that the square root itself isn't actually necessary. So we will let x be 1 times tangent of theta, and therefore dx is the derivative of tangent, secant squared d theta. So we have dx, which is secant squared theta d theta, divided by 1 plus tangent squared theta. And so that's secant squared theta divided by, well, 1 plus tangent squared theta, I tan secretly, so that's secant squared theta d theta. Okay, well, this is just the integral of d theta. Well, that would be, of course, theta plus a constant. So what's theta? Well, theta, if we isolate it, would be inverse tangent of x. So this comes out to inverse tangent of x. And of course, we knew that all along, so we're done.
It's working!
Oh.
You did it! It's working!
All right, let's give this one a shot. Now, we do have a difference of squares here, and it's inside a radical. This is a form that strongly suggests using a trigonometric substitution. But never forget to always spend a moment looking for an obvious u substitution. For instance, if this were x times radical 9 minus x squared, then suddenly it's got a nice obvious u substitution. We would let u equal 9 minus x squared. The derivative of that is negative 2x dx, and we have an x dx, so we know that we can handle this one very nicely with a u substitution. That's not to say that this particular one wouldn't work also with a trigonometric substitution, but I think it's evident that a trigonometric substitution is just inherently more complex than a basic u substitution. For this particular example, it's not obvious that a basic u substitution exists or that integration by parts will be particularly helpful. We do have the form for a trigonometric substitution, so I say we just go right in and do that. So what are we going to let x equal? Well, based on the form, we have a number squared minus the variable squared. So the suggestion would be to let x be, in this case, 3 sine theta. And we're no longer going to write the restrictions. We're going to assume that we are restricting theta such that we get a positive value for the cosine of theta. So that would, in this case, be the first and the fourth quadrant. So our dx will be the derivative of 3 sine theta, which would be 3 cosine theta d theta. Okay, so now we'll work on the integral itself. Here's the original. And applying the substitutions, we'll see that the radical part becomes 9 minus the square of x. That would be 9 sine squared theta. This is all over x squared, which is 9 sine squared theta. And dx becomes 3 cosine theta d theta. Remember, you don't have to solve for dx. The particular way that we create this substitution, we get dx isolated for free. So That is one upshot to this method. So, of course, now we have this mess of a trigonometric integral. Let's clean it up however we can and see what we've got. You can factor the square root of 9 out of the square root, so of course that's 3. So we have 3 times the square root of 1 minus sine squared times 3 cosine of theta. This is all over 9 sine squared of theta, and we have d theta. Okay, so 3 times 3 is 9, which cancels with the 9, so that's particularly convenient. Let's see what else happens. The 1 minus sine squared is cosine squared. The square root of cosine squared will be cosine, so we have in the numerator cosine times cosine, which is cosine squared of theta. In the denominator, we have sine squared theta. Okay, well, what is this? Cosine over sine is cotangent, so this is cotangent squared theta d theta. So you can see we've dropped it down to a nice simple trigonometric integral. Well, how do we integrate cotangent squared? Right? Well, cotangent squared, we can write it as cosecant squared of theta minus 1, because we do know how to integrate cosecant squared, and of course we know how to integrate 1. Antiderivative of cosecant squared happens to be negative cotangent. So that's convenient. What we have is negative cotangent of theta minus antiderivative of 1, which is theta, plus our constant. So the last step of this would be simply to convert everything back over to x, and we're going to need a triangle to do that. So let's look at the original substitution. X is equal to 3 sine theta. Well, this means that sine of theta is x over 3. So placing our theta in the triangle, we know that sine concerns the opposite side over the hypotenuse. So if sine of theta is x over 3, then we'll label the opposite side x and the hypotenuse 3. And using the Pythagorean theorem, we'll see 3 squared is 9, x squared is x squared. So we have the square root of 9 minus x squared as the missing side. Okay, so now we can read off the triangle, sine, cosine, tangent, whatever, of theta. And in this case, we want negative cotangent of theta. So according to the triangle, cotangent of theta would be adjacent over opposite. So we have radical 9 minus x squared divided by x. That's what cotangent of theta is. Now we will subtract simply theta. Okay, well, what the heck is theta? Well, again, going back to our substitution, we can see that if sine of theta is x over 3, then we can call theta the inverse sine of x over 3. So, very good. That is our final answer. Okay, so for this one, we sort of have the form of a trigonometric substitution in the sense that we have something squared minus something else squared. However, this too is a little troublesome because it's not just x squared, it's like 2x squared here. So we have several options for handling this. One is that you can factor the 2 out first, so we get x squared minus 2 times 2. This is all occurring within the radical, and then you can actually just factor that rad 2 completely out of the integral, and now it's no longer a problem. And from this point, you would say, okay, x squared minus a squared. We would let x in this case be a times the secant of theta. So we would go x is equal to a, which would be rad 2 times secant of theta. And we'd be on our merry way. So that is one way to handle it, and a perfectly good way to handle it. An alternative way to handle this is to say, all right, look, wouldn't it be nice if we just had u squared minus 4 right there? Because if we did that, then we could just let u equal 2 secant of theta and be on our merry ways from there. And indeed, that would be wonderful. And we can make that happen by using a u substitution. So let's do that approach. So what we're going to do is we're going to let u be the square root of 2 times x. The reason why we're choosing that is because we want u squared to be 2x squared. So this means that our du is the square root of 2 times dx. Okay, now this is a classic u substitution, so we should isolate our dx, and we get dx is du divided by square root of 2. So returning to our integral, we're going to get a new integral, and we'll have u squared minus 4 divided by x. Well, we can see that x is u over rad 2, and dx is du over rad 2. Okay, let's also update the bounds of integration. When x is the square root of 2, we can see that u is square root of 2 times square root of 2, which is just 2. And when x is equal to 2, we can see that u is 2 times rad 2. And there's our new integral. But look, these square roots of 2's cancel. That's convenient. So our integral becomes simply the integral from 2 to 2 rad 2 of radical u squared minus 4, all divided by u, du. And again, the form here being variable squared minus a squared means that we should let u be a, which in this case will be 2, times secant of theta. So du will be 2 secant of theta, tangent of theta, d theta. All right, let's see what this does to our integral. So we have the integral of square root of u squared, which is 4 secant squared theta minus 4, all divided by u, which is 2 secant of theta, and our du is 2 secant of theta, tangent of theta, d theta. What about our bounds? Well, they need to be updated again. These are u values. So when u is equal to 2, we can see that secant of theta will be 2 divided by 2, which is 1. So secant of theta equaling 1 means that theta is 0. And when u is 2 root 2, then secant of theta is just the square root of 2. So what angle has a secant value of rad 2? That is pi over 4. Okay, and we do get a little more cancellation at this point. So where are we here? We are at integral from 0 to pi over 4. The square root of 4 can factor out of the radical, so we have 2 times secant squared theta minus 1. We have another tangent of theta factor, and d theta. Okay, but this was perfectly contrived so that this radical expression would reduce to a single trig function. Of course, secant squared of theta minus 1 is tangent squared, and the square root of that will be tangent. So tangent times tangent will be tangent squared. So we are now at integral from 0 to pi over 4 of 2 tangent squared theta d theta. Okay, so 0 to pi over 4 of how do we integrate tangent squared? Well, we write that as secant squared of theta minus 1 because we know how to integrate secant squared and we know how to integrate 1. I'm going to spend a moment just distributing. And now we'll integrate. So this becomes 2 times tangent of theta minus 2 theta from 0 to pi over 4. We do not need to roll the substitutions backward because this is a definite integral, which means we've been updating the bounds as we go all the way down. So we just need to plug in 0 and pi over 4 directly in for theta and we'll get the right answer. So for pi over 4, we'll have 2 times tangent of pi over 4 minus 2 times pi over 4. And we'll plug 0 in. We get 2 times tangent of 0 minus 2 times 0. Okay, well, tangent of 0 is 0, 0 there, so that whole right thing is 0. Tangent of pi over 4 is, of course, 1, so this is just 2 minus pi over 2. And that's the correct answer. All right, let's do this one here. So we can see no obvious u substitution. Well, let's go into a trig substitution here. So x squared minus a squared, in this case, we will let x equal a times secant of theta, like last time. So here we'll let x equal, well, here our a is 1, so we'll just let x equal secant of theta. So dx is secant theta tangent theta d theta. Okay, so how does this affect our integral? Well, we're going to get secant squared theta minus 1 divided by secant cubed of theta, and our dx is secant theta tangent theta d theta. Okay, so this cleans up. In the usual way, we have our radical of secant squared minus 1. We know that's going to be radical of tangent squared, and which will just be tangent. So tangent times tangent will be tangent squared. This secant factor cancels with one of the secant factors from the denominator, giving us tangent squared divided by secant squared. And there's our d theta. Okay, but tangent itself is sine times secant. So this is really sine squared over secant squared, which means this entire integral reduces to simply sine squared theta d theta. So we have kicked down this integral to simply integrating sine squared theta. So how do we integrate sine squared? Well, it's a good thing that the immediate previous section was integrating powers of trigonometric functions. We know how to integrate sine squared. We shouldn't have to even think about it. We immediately reach for the prescription here, which is to convert sine squared into 1/2 of 1 minus cosine of 2 theta. All right, so let's integrate each term here. This integrates to 1/2 theta, and cosine integrates to sine, and of course we know that there's another factor of 1/2 that will emerge, so this will be 1/4 sine of 2 theta plus our constant. So all we have to do is draw a triangle and convert back in terms of x, right? So we go back to our original substitution, and we see that x is secant of theta, so let's draw a triangle here. And we know that secant of theta is x. Secant concerns the sides hypotenuse over adjacent, so let's label x over 1 there, so secant of theta is x. And using the Pythagorean theorem, we will get the missing side, so that's hypotenuse squared minus the other one squared, so radical x squared minus 1. And now we can read off this triangle, sine, cosine, tangent, whatever. The problem with this particular expression is that we do not have a triangle with 2 theta. That's a completely different angle. We only have the triangle with the original theta. So for this type of situation, we're going to need one more trigonometric identity, and that's the double angle identity for sine. So 1/4 of sine 2 theta is in fact 1/2 sine theta times cosine theta. And we used the fact that sine of 2 theta is 2 sine theta cosine theta. So yeah, pretty much everything you ever learn in trigonometry comes back in calculus, right?
Everything? Everything?
Everything! Everything!
Everything.
Everything.
Everything. Everything.
Everything in the solar system and everything.
Everything!
Everything.
All of it.
Now we have all these trig functions in terms of simply theta, so we can pull their value off of the triangle. So 1/2 of theta. Well, theta itself is inverse secant of x. So this is going to be 1/2 inverse secant of x minus 1/2 sine of theta. So sine of theta, opposite over hypotenuse, times cosine of theta. Cosine of theta is 1 over x, adjacent over hypotenuse. We can clean it up a little bit. We get 1/2 inverse secant of x minus rad x squared minus 1 over 2x squared plus our constant. Okay, now this one is very interesting because we have this little x in here. So if that x weren't there, let's just get rid of it for a second. Let's say we didn't have the x there. Then no problem. This is a very straightforward trig substitution problem. We would let x equal radical 2 times sine of theta and proceed from there. However, we do have the x there in this problem, and therefore we can't just regard this as a squared minus x squared, because it's not a constant squared minus x squared, it's actually a linear term minus x squared. So to handle this situation, we need to pull out a move that you probably haven't used in a good while, and that is completing the square. So, okay, let's lift this thing out, and we're just going to write it as negative x squared plus 2x, so it's in descending order. And let's factor the negative out, so the leading coefficient is positive. And the thought process behind completing the square is that you take the linear term's coefficient, in this case negative 2, you divide that quantity by 2, so we get negative 1, and then you square it, so we get positive 1. And that's what you add and simultaneously subtract in order to create a perfect square trinomial. So if we partially distribute the negative, we'll have negative of the trinomial, and then negative negative 1, so plus 1 on the outside here. And this trinomial is a perfect square of x minus 1. So returning to our original integral, we can see that this is in fact simply dx divided by the square root of 1 minus quantity x minus 1 squared. Now we have the form of a constant squared minus something else squared. It'd probably be a good idea just to do a quick u substitution here. So we'll let u equal x minus 1, and therefore du is dx. So this is du over radical 1 minus u squared. Now, I really hope that you can recognize this as inverse sine of u, because if you do recognize it as inverse sine of u, then we are basically done the problem. We just replace u with x minus 1 and we're finished. But let's suppose we don't recognize that as the derivative of inverse sine. So we're going to actually carry out the u substitution. So now we're going to let u equal sine of theta, because this is of the form a squared minus u squared. So du is cosine of theta d theta. And we get cosine of theta d theta, that's our du, all over 1 minus sine squared. Well, 1 minus sine squared theta is cosine squared theta. The radical drops it down to just cosine. So we have cosine theta over cosine theta. That is simply the integral of d theta, which of course integrates to theta plus a constant. And looking at our substitution here, we can see that if u is sine theta, then theta is inverse sine of u. So we have arrived at inverse sine of u through the process. Remember that u is equal to x minus 1, so our actual true answer is inverse sine of x minus 1 plus our constant. And we're done. All right. With this one, I think we can all agree, just by looking at it, that we're probably going to have to start with a u substitution. We have the 1 plus stuff squared, and we'd really like that just to be 1 plus u squared. If we had 1 plus u squared in there, then we would proceed just by letting u equal tangent of theta and seeing where that leads us. So of course, how do we make it so it's just 1 plus u squared? Through u substitution. So if we want 1 plus e to the 2x to equal 1 plus u squared, we can actually use this particular statement here to inform exactly what our u substitution should be. First of all, we can cancel the 1's from both sides, so we have e to the 2x is equal to u squared, and taking the square root of both sides, we can see that we are going to get u equal to e to the x. So we now know that that is the u substitution that we want. And of course, therefore, du is e to the x dx, which we happen to have. So this is jingles. All right, this becomes the integral of e to the x dx is simply du. And we have the square root of 1 plus u squared. Well, we're used to writing du on the far right, so let's certainly do that so we can stop shaking. And how do we integrate this guy? Well, we're going to do the u equal tangent substitution. So u is equal to tangent of theta, and du will be secant squared theta d theta. So under the radical, we have 1 plus tan squared theta, and then du is secant squared theta d theta. Of course, as always, this entire radical expression will drop down to a single trig function, and in this case, it'll drop down to secant of theta, which means we have secant of theta times secant squared. Well, of course, that's secant cubed of theta. Okay, so the next question we have is, how do we integrate secant cubed? Well, the good news is we integrated it in the last lecture. So let's borrow that result, and we can see that this immediately becomes 1/2 secant theta tangent theta plus 1/2 ln of absolute value of secant theta plus tangent of theta plus c. Had we not evaluated secant cubed integral in the last lecture, we would be burdened with doing that right now. And that involved integration by parts. That involved a boomerang. So it was not a straightforward integral. Now, you're not meant to memorize this integral. We're just taking advantage of a nice coincidence that we worked this out already to save us some time. Okay, so all we have to do is drop everything back down to x. So of course we're going to need a triangle, and we know from our substitution here that u is equal to tangent of theta. So if tangent of theta is u, then the opposite side we'll call u, the adjacent side we'll call 1, and the hypotenuse will be the square root of 1 plus u squared. And now we can read sine, cosine, tangent, whatever of theta off of this triangle. So secant of theta is hypotenuse over adjacent, so that will be the square root of 1 plus u squared. Tangent of theta we know is of course just u. And secant of theta is the square root guy again. Tangent of theta is just u. Okay, so we're not quite finished because we also need to drop the u's back down to x's. And if you recall, u is e to the x. So what we really have here is 1/2 u, which is e to the x, times the square root of 1 plus u squared, that would be 1 plus e to the 2x, plus 1/2 ln of, now we know this is going to be a positive expression since the u's are always positive, since they're equal to an exponential. So we can get rid of the absolute value, 1 plus e to the 2x plus e to the x, and plus our constant. And it's not the cleanest expression in the world, but that is the correct final answer.